Welcome back. Happy Wednesday. Today is April 27th. We are covering something called Taylor polynomials, brand new topic today, but we will relate yesterday's class and today's class when we get to next class. So they're going to come together next time. Just looking ahead a few days from now, counting today, we've got 3 more days of new material before our third and final test. So 3 days of new material, then a review day on May 4, and then May 6th is our test. Project number 8 is due coming up May 2nd, which is Monday. Questions on the calendar? I will grade the quizzes and give them back to you soon, but I don't have them just yet. Okay, so starting here on the top of page 47 with our summary. In this section, we meet Mr. Brooke Taylor and his polynomials. Our goal is to create a polynomial whose behavior near x equals a is just some number, agrees with the behavior of a random, messy but differentiable function as closely as possible. So today we're going to be playing around with e to the 2x. That's going to be the formula we play with here. We'll start with a function e to the 2x. E to the 2x is decidedly not a polynomial. Agree? Right. We're going to try to approximate e to the 2x. E to the 2x is just an exponential growth curve. We're going to try to approximate this e to the 2x with the polynomial. Now that's kind of a problem because we know e to the 2x has this asymptote of the x-axis. And polynomials do not have asymptotes, right? They go forever up or forever down, but we're going to do our best. So that's the goal for today. And instead of starting with e to the 2x, maybe we start with cosine, which again is decidedly not a polynomial, but we're going to try to approximate it with a polynomial. Okay, that's the goal. Question? No. Okay. Okay, so number 1, consider the function f of x equals e to the 2x. So I'll highlight it because we're going to be playing with this function for a while today. In this demo and activity, we will explore how f can be approximated by a polynomial. Do not consult any formulas from chapter 10. We are going to build them as we do the demo and activity. So number 2, let p sub 1 of x be a degree 1 polynomial. That means it's linear, so x to the first. And so in general, we know that linear things are typically written as y equals mx plus b. Yes? I'm going to write it in that order. And instead of calling it b and m, we're going to call it a0 and a1. Just turns out that even though it looks messier with a0 and a1, it's going to allow us to do things more generally, right? So a0 and a1 are just numbers, they're constants to be determined. Highlighting here that the calling it p sub 1, that 1 is supposed to match the degree, which is the power of 1 up there, right? So lots of notation here, but it all has there's a goal for all of this at the end of the day. So let us compute f of 0 and f prime of 0. F is again highlighted up here at the top. F of 0 is e to the 2 times 0, which is 1. Great. So that's f of 0, it's 1, easy. To find f prime of 0, well, first we need to find f prime of x. Right? So what's the derivative of e to the 2x? Yeah, so I'm going to write e to the 2x and then chain rule says times 2. So there's f prime of x. For some reason, we want f prime of 0, so let's find it now. E to the 2 times 0 times 2, which is 2. So far, so good. And the 0 that was mysteriously introduced in this problem is the value of a. It's just going to be given. Is that? Yeah, I think that's good. Maybe better is this. A equals 0. It's just going to be given in the problems. So it's just a starting value for us. Okay, so now what we're going to do is compute p1 of 0 and p1 prime of 0. And currently p has nothing to do with the f function up there. So we're just, I'll highlight in a different color here. There is p1. And so we're just going to plug 0 in. So p1 of 0 is a0 plus a1 times, instead of x, 0. So how much is that? a0. So far, so good. And then we're looking for p1 prime of 0, but first we got to find the derivative for x. So what is the derivative of that highlighted blue function? It's just a1, right? Just the number touching the x. So it's just a1. And then according to this problem, we're supposed to plug 0 in to that thing. Now, there's no x's in this one, so there isn't really much to do, but that's just sort of a fluke. So p1 prime of 0 is how much? It's just a1. But if there were x's floating around, you would put 0 for the x's. F prime of x for the second? Not sure what you're asking. Why we're using f prime? So in the next step here, what we're trying to do is take our e to the 2x, this exponential growth thing, and we're going to approximate it with a polynomial. In this case, we're going to approximate it with a linear polynomial. And so in order to approximate this guy with that linear function, what we're going to do is we're going to pick a value of x, 0 in this case. Okay, so that's just the y-intercept of my exponential. And what we're going to do right now is we're going to pick a0 and a1 so that two things happen. Number one, my exponential, my arm is just not flexible enough to do what I want. So let's try this. That's what we want. Yeah, so what we're trying to do here, that picture is not so great. What we're trying to do, there's our e to the 2x. What we're doing is making the y value the same, and we're going to make the slope the same. So the slope of that curve and the slope of our P1 formula, we're going to make them equal to each other. Like we were trying to find a derivative at a point. You envision the line, the curve. Yeah. I don't see that here, but it doesn't mean, it might just be that I'm not making the connection that you are. So let's talk about that in a little bit, but let me keep going here and you tell me if it kind of jives with what you're imagining. So part C, it says, we are going to equate things. So let's see, we're going to highlight in green. F of 0 is 1. P1 of 0 is A0. We're going to make them equal each other, okay? It's just part of the process. So A0 equals 1. That is what we are defining right now. Just make them equal. A0 equals 1, color-coded in green. And then the other thing we're going to equate is F prime of 0 with P prime of 0, okay? So what equation does that boil down to? A1 equals 2, that's all. We're just making things equal each other, and we're done. A1 is 2, highlighted in blue. Okay, it's part of the process. As you make them have the same y value, you make them have the same derivative. First thing in the activity you'll do on the next page is make them have the same second derivative. So we're just going to make them equal each other every step of the way. Okay, so just rewriting our formula here. P1 of x, I'll copy it from above. It was A0 plus A1x. That was where we started. And let's just change A0 and A1 to the numbers we just calculated. So this becomes what? 1 plus 2x. And that line, what does it have to do with the original graph of this e to the 2x up here? Yeah, so it's got the right value, so it's going to go through that same green point there, and it's going to have the same slope as the black curve. So what am I drawing? What line am I drawing? The tangent line. We just made the tangent line. So that thing, that's what you're thinking. Okay. All right, so that right there is P1. That's the tangent line. Just thinking of it in a slightly different way. I mean, you found tangent lines a bunch last semester. But on the next page, you're going to start by finding the quote tangent parabola. You're going to find it the best x squared kind of thing. This was just the best linear thing, okay? All right, so I think that that is it for the demo. So you are going to, so up until now it's review, and then this is new. Start. I don't think that we've approximated a function by a quadratic before. Certainly we've done tangent lines before. We did linear approximation. We actually might have done a quadratic. We might have done a quadratic on the, yeah. I didn't teach Calc 1 last semester, so I don't know. Yeah. What we did was we set f of 0 equal to p1 of 0. Yeah. Okay, so the activity is long. You got lots of time. Let's see what we can do.